So your cinnamon rolls.
On page 360.
Did JR tell you about the joke?
No, it was so disappointing. The whole cinnamon bun issue.
Okay, we had this plan.
We had a great plan.
We had this plan that like JR put it on another plate and then you put the cinnamon bun in like one of the drawers, and then when you came back we were like
It was
everybody
gonna
was
be
gonna
gone.
yeah,
and we were
everybody was
gonna
gonna
blame
say that I ate it. Cause you know how I was like I kept
We weren't gonna say it. We were just going to see who you suspected and like.
It was gonna be Connor and Brett.
Yeah.
No, because I kept on asking for the cinnamon bun and then like I kept on asking for
Yeah,
bites.
but like I feel like Connor is like more bold to do it.
And guess who
Jared-
ate the cinnamon
Jared
bun in the end?
Connor.
Eat it.
Did he actually?
We wanted it,
Yeah.
and we felt this pain of guilt.
Yeah.
It
was really tempting. It was like-
the whole thing.
It's like the green account in the Bible.
Anyways, okay. So we're on page 360. Compound interest. One of the ways that exponential functions show up in real life is with compound interest. So they've got an example here. They say consider an investment of $100 in a savings account that pays 2% annual interest compounded annually. So what does that actually mean? That means if you did this with your bank, you would start off with $100. Woohoo! You are so rich. And then at the end of the year, they give you 2% interest. So 2% of $100 is $2. And now at the end of the year, you have $102. And the way that compound interest works says, well, now you have $102. So now at the end of the year, they're going to pay you 2% again. Well, 2% on the $100 that you originally had is another $2. And 2% of the $2 is 4 cents. So having that extra $2 in there means that the next year you got 4 extra cents.
Wow.
Wow. And the year after that, you would get, well, on the $100, you would get another $2, so you're at 106. On the $4, you would get another 8 cents. Added to the 4 cents would 12 cents. And on the 4 cents, you would get another 8,000th of a cent into your account, which they would just ignore
We're rich.
and not be there.
Would that still be in the next calculation?
It would be in the calculations if things stayed and kept going, but on your bank account, it probably wouldn't.
Okay, they better give me 13 cents instead of 12 then.
And it's not even close to 13 cents.
Oh.
Right. I'm sorry. But if it did get to 13 cents, that would be huge, because if you ask for a payout, there's no pennies, they'd have to give you 15 cents. But this one, they'd only have to give you 10 cents.
We can send a chip to the bank.
Oh yeah, it's like, I'm waiting till that extra penny goes in there, I'm gonna take out my money, and then I'm gonna invest it again the same day. That's strategy. Yeah, oh, you could, oh, this could work. We could make millions, hours and hours of work, and we probably could make 25 cents by the end of the day. Maybe this is good. Anyways, this is the idea of compound interest, and what's happening each time is that you are multiplying by 1.02. And if you take this and multiply by 1.02 again, and that is exponential growth. In fact, we could write our equation. We started with $100, then we multiplied by 1.02 X amount of times. It doesn't really go crazy in 4 years. You're like, woo, $6, right?
Well, if you got some more money in there.
But what do all exponential graphs look like? They look, if this number is bigger than 1, they all have an asymptote here. They all go through 0, 1, but this would have a vertical stretch by 100. So now we have the point 0, 100. as our starting point. And exponential graphs go like this. And eventually do this part. With money, that's when you get into the exciting part, right? What is this right now is like, it's actually probably more like this. We're in this boring part where, oh, $2 more every year. But if we graphed it, right? Alright, so you find out, there we go. Go to our graph, we go to our equations, we clear this out. 100 and then 1.02 to the exponent x, okay? And I'm gonna set my window up from -1. We'll just look at 10 years. -1. We know that it starts at 100, so I'm gonna just look up to 120. No, it's gonna go 10 years at $2 a year. We're gonna be more than 120. We're gonna just make it look like 200. Okay? And if we look in that first, it's pretty flat. Okay? 10 years, it hasn't gone up crazy. Does it look like an exponential graph at this point? Not really. But if I change my window, right, 1,000 years. No, I went 1,000, and then I'll look up to 1,000 now. Let's see what happens. Ooh, it has that curve a lot more, right? Okay.
How much are we at?
So you found out you had a relative who owned a bank 1,000 years ago. This is very realistic,
Oh, no.
right?
This happened to me.
And they put $100 1,000 years ago, which would have been a lot of money. But they put $100 1,000 years ago for you in that bank account at 2%. And at the beginning, they were giggling because like, oh, it's not really my $102, $104, $106. Wasn't really that much. But now they're like, sorry, the bank is closing. You have to take your money out. They're forcing you to take out this $100 investment 1,000 years later. So we just want to calculate what is the value of it 1,000 years later, and you just happen to pull out 3.9826 e to the 10. Do you know what this e to the 10 is?
10 zeros.
Scientific notation, so we would have to do like, go back here. 3, 1, 2, I'll just round 3, 4, 5, 6, 7, 8, 9, 10. Is that a good amount of money to take? Oh, I wish I found this dead relative. Would that be a nice amount of money right now to pull out? Just 39 billion? Be like,
That would solve my problem.
right? Hey, Elon, Jeff, you wanna go out for lunch?
Yeah.
Right?
Yeah.
Might be that island.
What's that?
Files.
That's a lot of money. So initially, not very much. But once it got into that exponential growth stage, it started going crazy. So with investments, even if your percentage is low, over time, it can get a little bit crazy. And we're going to look at some of those things when we're dealing with our math. We have a compound interest formula. The nice thing, there is so many real life, let's see what's on the next one. There's so many real life applications to exponential functions that they decided not to put any on your formula sheet. Which is kind of nerve-wracking. It's like, do I have to have this formula memorized? No. Instead, they used to put 3 or 4 formulas about exponential stuff on your formula sheet, and you have to know how to use them. Now, they say we can put any question we want on the exam that uses exponents. We will also give you the formula and explain what it means. So if you got a question with compound interest, they would give you this formula and tell you what each of the things mean. So as long as you can do the math, you have the formula given to you. You just have to plug things in to the right places. And compound interest ends up being an exponential function of that form where if your interest rate is positive, which most of them are, it's going to be a growth, and it's gonna have, anytime you have growth in an exponential function, it has this shape. And if you leave it in long enough, you get to take this advantage. So sometimes people say, hey, start investing now, right? In fact, probably the problem with investing is you need to have money to invest. And the problem is life. You need to have money to live. And usually they try to take more money for living than they let you keep at the end of the day. So it makes things a little bit difficult. But Canada has something, I think once you turn 18, Canada has a tax-free savings account. And if you can start putting money in that early, at a certain interest rate, it will just keep getting bigger and bigger and bigger and bigger. Problem is, you'll get tempted in life to be like, I owe a lot of money for something, I should take it out, right? But as soon as you take it out, you're getting rid of that chance for that growth to happen. A principal of $1,500 is interest at 4% annual interest rate, compounded quarterly. So what would happen is that they would give you this formula, and I'm writing it with slightly different letters. They can choose whatever letters they want. The formula that was in your textbook had A0. Sometimes formulas use P for principal. And then they would tell you what each of the things are. I'm not going to write them all down because I don't want to waste time, but they tell you that this is the amount after T years. P is the principal. They would tell you that R is the interest rate as a decimal. N is the number of compounding periods, and T is time in years. So then based on all of that, you'd say, oh, I have the principal part, so I can put $1,500, I don't even need a bracket there. I can put 1,500 in for the P. 1 plus, I know the interest rate is 4%, I can change that to 0.04. Oh, look at my plus sign, they decided. Oh, there it is. Divided by, now the number of compounding periods per year can be tricky because you need to know some English language. So this one says quarterly. Quarterly is how many times per year?
Every 3 months.
Every 3 months, but how many times would that be?
4 times.
4 times per year. So that makes this a 4. The most common one that they have is monthly. Monthly would be 12. They could say daily, and you'd write 365. Some of the tricky ones are semi-annually. Do you know what semi-annually means? Every 6 months, which would be how many times per year? Twice. What about,
Oh, I have to get the.
right? So that happened on an exam. It had semi-annually. People are like, what does that mean? We're like, I'm sorry, they expect you to know all of those. So semi-annually is twice a year. Monthly, 12, daily, 365. Quarterly, 4 times a year. What would be some other? Bi-weekly, every 2 weeks. How many weeks are there in a year? 52. So bi-weekly would be 26. I've never seen bi-weekly though in the exam. I have seen semi-annually. I've seen annually. Annually is a tough one. How many times per year? Once. Okay. And so I put in the 4 there. I'd also put a 4 there, and I don't know the time. I do know that the amount needs to be 2,500. And herein lies the problem that's going to be solved by this unit. The problem that's going to be solved by this unit is you do not have the skills to get T by itself. It's a common thing in math, solving equations. Right? 2x plus 5 equals 7. You have the skills to combine like terms, move things over from one side to the other. You have the skills to solve for x in a lot of places, except when the x or the variable is in the exponent. We just learned that if we can put these in a powers chart, okay, just double check. Was 1.01 in your powers chart anywhere? No. If you can have them in your powers chart, if they choose nice numbers, we could do it. But if the numbers chosen are not nice, we actually don't have the mathematical skill yet to do that. We're going to learn that in this unit. But as of right now, the only way you could solve this is with Desmos or a graphing calculator. In which case, you would type this into y1 and this into y2 and hope you can find out where they cross each other. So I'm going to take out my calculator. You could also type y equals 2500 and y equals this into Desmos and find out where the two graphs intersect. So I'll show you that on your calculator because it is an important skill for AP Calculus. So I'm going to go to y equals. I'm going to clear it out. One of them was 2500 and the other one was 1500 bracket 1 plus 0.04 divided by 4 to the exponent of 4. And there's my variable x. Those are my two equations. My first equation is a straight line at 2500. So I'm going to go to my window and make sure my y max, I'll go up to 3000. I want to make sure that I can see that 2500. In fact, I'm going to hit graph right now and like, ooh, they almost crossed. You see how close we were? This exponential graph was increasing. What did I need to do? I need to go further along there. So I'm going to hit my window button again. And I'm like, I think by 20, it will have hit. Yes, it does. So I took a guess. Now that they've intersected, I can go second, calculate. Where do these intersect? Of course, on Desmos, you just click on one of the graphs and that dot will appear. But I push enter on my first curve, enter on my second curve, enter to guess. 12.834. So t equals 12.834. Years was my units. I should double check. I rounded to 3 decimal places naturally because everything, if you don't know, you do 3 decimal places. Then I read the question. It says to the nearest quarter of the year. Whew. Is this closer to 12.75 or 13? If I was rounding. Is 0.83 closer to 0.75 or 0.00? It's closer to 0.75. 8 away from 7.5. It'd be 17 away from 13. So, to the nearest quarter of the year, this would be 12.75. Oh, you know what's great about the next question? I'll get you to circle ones first here. This is, can circle 12 and 13.